Okay, so welcome to class 4. So let's get started. Today we're doing, I think, probability. It's like combinatorics, but probability and expected value. Okay, so for probability basics, so I'm sure you guys all like understand what the definition of a probability of an event is, but okay, here are two ways we can represent it, right? And then it's equal to the fraction of possible outcomes, which correspond to A. And how to find it, we count all the possible outcomes, and then we count all the desired outcomes, and we divide like all the desired ones by all the possible ones. All right, so for the very first example problem I'm going to do, so without any like a break for you guys to solve, and then for the later ones, I'll give you guys time to like think about it, and then we'll talk about it. All right, okay, so the first one, it asks, what is the probability that a 5-card poker hand contains exactly 2 aces? Okay, so how many aces are in like a deck? There are 4 aces, right? For each of the suits. So by choosing 2 aces, we can first count like all the desired outcomes. So how many ways are there to take 2 aces from 4 total? That's 4 choose 2. Okay, wait, let me write it as. So desired, choose 2 aces. 4 choose 2, which is 6 ways, right? Okay, and then we choose the other 3 cards. So there's 48 cards that are not aces, and we have to choose 3 of them because we've already chose 2 out of the 5 as aces. Okay, and this equals, let's just do this split. Okay, equals this number. All right, and then the total number of possible hands is found by choosing 5 cards out of the deck of 52. So let's do total. Right, and we don't have to calculate this all out. The problem does not. It's okay, like, because this is like gonna be a super long computational problem. So what we have to do is just multiply these two numbers and then divide by our denominator, which is this. So our final answer is 6 times 8 times 47 times 46 over 52 choose 5. And you can calculate that out if you want to, but they're like really big numbers. All right, any questions? Okay.
I have a question.
Yes.
How did when you put desired choose 2A out of 4 total, how did you get 4? I thought it was a 5-card poker.
Oh yeah, good question. So first we're choosing like the aces, right? Because we need to have 2 aces in our 5 cards. So there's 4 total aces in the deck, right? So sorry, this means like 2 aces out of 4 total aces.
Oh, I wouldn't know that there were 4 aces in the deck.
Oh yeah. Well, it's good to know because there's 4 suits and then 13 in each suit. Right. Okay. And then do you understand how why we multiply like 6 by multiply these two numbers? Because they're kind of independent events, right? Like you choosing 2 unique aces does not like it's independent with choosing the 3 remaining cards that are not aces. Okay. So let's take like 2 minutes to for you guys to look at this question, and I'll ask someone for their ideas on it, and then like show the solution to the whole class. And like as a note, value means like there's 13 different values. It's like 2 to 10 and then Jack, Queen, King, Ace. And they're like 13 different values of each suit. So like 4 suits of every value. Oh yes, Evelyn?
Are there questions on the homework that involve like poker cards? Because I don't know much about poker. And for the other question before, you had to know that there were like four aces in the deck.
Um, I don't make the homework, so I'm not sure, but I can tell like you guys' TA to not include many questions about poker cards. Is that okay?
Okay, because I don't know anything about it.
All right, does anyone have any ideas on this question? Oh yes, bye-bye.
So, I guess this is just an idea, but like 4 out of 52, because I guess each of the like face values have 4 of them.
Mm-hmm.
So 4 over 52 times the second one would be 3 out of 51. But then there are 13 of those pairs, so I guess you multiply that by 13. I'm not sure if it's right.
Yeah, okay, so you're saying like 52 choose 4, and then times like 51 choose 3,
Yeah.
and then multiply by 13.
Yeah, that's what I'm thinking about.
All right, yeah. So is that your like that's your desired what is it? Like desired total, right? And then do you have a value for like the total number? Because we're calculating a probability, right?
So that would be 52 times 51 times 50 times 49 times 48.
Mm-hmm. Yeah, so that's almost there, but I think we can do 52 choose 5 because at the top you did like choosing, so like order doesn't matter. So when you do like for your numerator, if you do like choosing and not like what is it, permutations, you should do the same like what you did for the denominator. So I would do like 52 choose 5. It's like the same thing, but like if your top number cannot be ordered, like if you make it so that your top number is not ordered, then you should also do it for your bottom number.
Okay.
Okay. So yeah, I think this is pretty good. Yeah, and then you would just leave it in this form. All right, so that is one way to do it, and I'll also say my way to do it. So first we can like pick the number which will be duplicated, right? So we can do this in 13 ways. So this is very similar. So like what we have, what I each said here. And then we can pick like two of the four cards of that number in 4 choose 2 ways. Right, so like 13 and then times 4 choose 2 because we pick like a value that to be duplicated and then there are 4 of those values, right? Because every value has a suit and we pick 2 of those values out of those 4 because we want 2 cards of the same value. Okay, and then for the rest 3 cards, we need them all of different values. So we choose like, so we do a 12 choose 3, and then because we have 12 remaining values and we choose 3 of them, and then we can choose like, and then we multiply it by 4 3 times because we have like 4 different suits in every one of those values. And then the denominator would be the same. So I think this turns out to be the same numbers, but yeah. Okay. All right, so next, multiplying probabilities. As I've mentioned before, if 2 events are like independent, we can also call them uncorrelated. And to calculate the probability of like both 2 uncorrelated events happening, we multiply their probabilities together. So we can do that for independent events. So like what are some examples? Example is like if event A, we say like a coin lands heads on first flip, and in event B, we say coin lands, say tail on the second flip. These 2 events, A and B, are independent. So like whatever happens on in A doesn't affect what happens in event B. All right, so for our example, we'll do this example. So 3 6-sided dice are rolled. What is the probability that at least one comes up with a 5 or 6? All right, so the way I'm going to do this is use complementary counting. So the probability of at least 1, 5, or 6, I'm going to say that is equal to the probability that is equal to 1 minus the probability of neither 5 or 6, right? Because neither 5 or 6 is easier to count, right? So like do this as 1 minus 4 over 6 times 4 over 6 times 4 over 6. Does that make sense? Because every time, like every one of the rolls for 3 rolls, we don't want 5 or 6 to come up, which means we can only have the numbers 1, 2, 3, and 4 to come up out of the 6 total. So if we multiply that 3 times, because they're independent events, right? We can multiply them because it doesn't matter when like whether of 1 to 4 rolls on the first dice or we roll 1 through 4 on the second time, like so we can multiply those probabilities together. And then after we get that, we want the opposite of that. We want like the complementary of that. So we subtract that from 1, then we get this number. Any questions? Okay. So we're gonna do some more examples now. So again, like I think I'll do these like the first question, it's pretty easy. It take like 1 minute, and then we'll come back, do the first question, and then do the last 2 questions because the last 2 are kind of related. Oh, yes, Evelyn.
How many of every shape is in a deck?
Um, how many of every what?
How many of each shape is in a deck?
13. It's like 13 in a suit, and then 4 suits.
Oh, I thought it was different for the shapes instead of numbers.
Oh, yes, my Bobby.
I think you paused screen sharing.
Oh, my bad. Okay. Is this good?
Yeah, now it's good.
Oh, yes.
Can I help answer the first question?
Yeah, go ahead.
So I think since there are 13 of each kind of cards, so it'd be 13 over 52 times 13 over 51 since one card's already picked out.
Great. That is the correct answer. So simplifying that, because this is 1/4, right? So this gives us 13 over 204. So just to reiterate, oh, very good, Vaibhavi, thank you. Just to reiterate, so like we have 2 cards drawn in order from deck of cards. If we want the first, it doesn't really matter that like it's a spade and a heart. It could be like a club and like a diamond, right? But like just to give names. So like the first is a spade, then there's 13 spades out of the entire deck. And the second one, there's another 13 hearts, but we're not choosing out of the entire deck, right? So the second time, we're only choosing out of 51 cards because we've already chosen a card. So that's like kind of the tricky thing you need to watch out for. All right, so on to the next 2 questions. I'll give these like 2 questions maybe 4 minutes total because they're kind of related. Yes, Violet?
Can I explain the second one?
Yeah, go ahead.
So if you want to choose a red one first, there'd be 3 ways of doing, like 3 different red balls you could choose. And
Mm-hmm.
same with the green, so that would be 3 times 3. And then the denominator would be 6 times 5. Because for the first option, if you're choosing anything, it would be 6, and then you would have taken 1 out already, so it'd be 5. So then
Great job.
divide is 3 over 10.
Yeah, great job. That is correct. All right, does anyone not understand that?
Um, does it make a difference, like, if they're asking what's the probability that red is chosen first, or does it?
Yeah, so for this, for the second question, it does matter like if the balls are chosen simultaneously or one after the other. Because I think for the second question, it's best to use, I think, choosing. So like you choose them at the same time. All right, does anyone have any ideas for the second question? So to help you guys get started, I think the denominator, so like our total number of possibilities, would be the number of ways to just choose 2 balls out of 6, right? So 6 choose 2. Because when we do choosing, order doesn't matter. And in this case, order does not matter. In the previous question, order did matter. Alright, and for the numerator, if we want 1 red and 1 green chosen, kind of like, how do I say this? Like, how many ways are there to just get 2 balls and then I think, okay, so I think the numerator in this question is still the same as the numerator in the previous question.
I set my answer in the chat because I'm not like 100% sure if it's right, but
Oh, yeah. So would you mind explaining like how you got there?
okay, is that right?
Um, you're almost there. How did you get your denominator?
So I did 3/6 times 3/6 because your total number of balls are 6, and then you choose 3 red balls and then 3 green, so 3/6 times 3/6.
But the thing is, like, after you choose the first red ball, there's not 6 left, right? And you can't calculate it like you choose one and then the next, because in this question, they're chosen at the same time.
Yeah. So, okay.
So I think what you're missing is that the total number of ways to choose just any 2 balls, which
Yeah.
is the total, like, this is the total denominator we're looking for, right? So just for the denominator, the total number of ways to choose 2 out of 6 is like 6 choose 2, which is 6 times 5 divided by 2. I mean, that would be the denominator.
15.
Yeah,
So 9/15.
yeah.
Okay.
So 3/5. All right, so yeah, these two probabilities are in fact very different because it's different from like choosing one and then the next. All right, so okay, let's move on to the next. Okay, now I'm going to talk a little bit about casework. So many problems in counting and probability come down to the, like you have to break things down to cases and count things separately within each case because some cases just do not work the same as others and you need to account for them separately. So to utilize this, we find the probability that each case occurs and then the overall probability is the sum of these. Because if your cases are like disjoint, you should make your cases disjoint, which means that they should not have overlapping outcomes. Because once they do not have overlapping outcomes, you can add them, like add their probabilities, which is very, like handy. All right, so firstly, what is the probability of rolling a 12 if 3 6-sided dice are rolled? And this means like rolling a sum of 12. Okay, so let's see. All right, I think the best way to do this is split it into, so we consider rolling the first 2 dice as 1 unit. This simplifies things a lot. And then the third by itself. All right, so, and then which configurations will give us 12? So we can have like 6, 6. So first 2 and then the third. We have 6, 6, 7, 5, 8, 4, 9, 3, 10, 2, and then 11, 1, right? Because the first 2 die, they can add up to 11 because it's 2 dice. And the third one, it can only go from 6 to 1. All right, so the probability of, okay, so if we were to get 6 on the first one, there's 5. Okay, wait, how do I? All right, so 5 over 36 times 1/6. And then this means like the probability of rolling a sum of 6 on the first 2 dice. Because you can have, okay, so like 1 and then 5, right? And then 2, 4, 3, 3, 4, 2, and then 5, 1, for a total of 5 cases out of 6 times 6, which is 5 over 36.
So why did you do 5?
You mean 5 in the numerator?
Yeah.
Because there are 5 desired outcomes.
Oh, okay. And then the 36, I'm just a little confused on that too.
Because the first 2 dice, there's 6 times 6 ways, right? Like total, like
Oh,
6 times 6.
okay, yeah, okay, thank you.
I have a question too.
Mm-hmm.
So so you got 5 for the first one. Just like suppose you get 6, like 7 or 8 or 9 for the next ones. So can't you just like add 5 and all of the other numbers and then get the overall count?
Add 5 and all the other numbers.
Like I
Oh.
meant like the numerator.
Oh yeah, but these cases they're not gonna give you 5, right? Because for 7, they're gonna give you, okay, so for 7, we can have like 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So that's 1, 2, 3, 4, 5, 6 ways.
So first, we just like calculate each probability then?
Yeah. And then does it make sense why I'm multiplying by 1/6 for this one? Because we want the third one to give us a 6, right? So that's happens with probability 1/6. All right, and then I'm just gonna like multiply everything out. So 6 over 36 times 1/6. This is for the 7, 5 case. I should have written it like this, sorry. So this is the 6, 6, and then the 7, 5. And then however, when it comes to 8, there are 5 cases again. Because you can't roll like a 7 on a dice, right? So it becomes, you count 6, like 6, 2, and then 5, 3, and then 4, 4, and then 3, 5, and then 2, 6. So that's 5.
So how come it's 6 over 36 for the 7 and 5 pair instead of 5 or whatever? Because 7, like, I didn't get that.
All right, I think that part you just have to count out. Like that just depends on what the number is, because to get 7, you can roll like a 1 and then a 6, and then you can count all the way up to 6, right? Like 3,
Oh,
4.
so you have to do that manually to like figure out every single pair? Like,
Yeah, I think that's
okay.
the best way to do it for like these simpler problems. For harder questions, you can kind of just enumerate it because for 7 you can go from 1 to 6. And
Yeah.
then and
Yeah,
then
okay.
for 8, however, you can't do like 1, 7. So you gotta go from 2 to 6.
Okay. Yeah, I got it. Thank you.
All right, and then to like keep on going because the numbers get bigger, the number of like possible ways to roll a 9 also gets lower. So for 9, 3, it's 4 over 36 times 1, 6. And then I'm gonna like right here. So 3 over 36 times 1, 6 plus 2 over 36 times 1, 6. And then this entire thing is our answer. It's 25 over 216. All right, any questions? So I think the casework part of this was breaking it into these 6 ways, right? Like 6 disjoint cases because they don't overlap. That's why we're able to add all of them. Okay. So for the next one, yeah, okay, I'll talk about odds. So odds are like kind of weird. They're defined as like the odds against an event A is the ratio of the probability that it does not happen. So like A, where was it? Like I forgot the wording, but like the complementary of A divided by like the total. So it's kind of a weird definition, but like to count to count the number of to calculate the odds for an event, aka calculating the odds against an event, we calculate the probability that it does not happen and we divide that by the probability that it does. So most of the time odds are like a ratio, right? So like I'm gonna do an example. So if a horse has a 7 in 100 chance of winning, so that's a 7 out of 100 probability, what are the odds against its winning? So the probability it does not happen, so like does not win is equal to 93 over 100, right? Because it's 1 minus 7 over 100. And then the probability that it does happen is 7 over 100. So to find the odds, we do 93 over, 93 over 100 over 7 over 100. Which gives like a 93 to 7 odds. So like kind of like higher odds are not good. Higher odds are not beneficial to something happening. Okay. Any questions?
No.
Yes.
No.
Sorry, I can't really hear you. I think you're cutting out.
No, I just said we don't have questions. That's
Oh, okay. All right, so last thing for today is expected value, and then we're going to do some exercises. So expected value is the average amount that someone can expect to get from like some game or activity where the activity depends on chance, right? So like to calculate it, we take all the possible outcomes and you kind of want them to be disjoint. So again, you can add them. You take all the possible outcomes and then multiply each by the probability of it happening and you add up everything. So like as an example, what is the expected value of buying stock in a small company if the stock fails with probably 1/2 is worth, okay, so fails with probably 1/2 means that it's worth $0, right? And it has probably 1/3 to be worth $1 and probability 1/6 to be worth $10. So how do we calculate this? So as the definition states, we multiply every event by the probability of that event times whatever value that event resembles. So just doing the math, I'm gonna get 1/2 times 0 plus 1/3 times 1 plus 1/6 times 10. Does that make sense? And this total gives us $2. So this kind of means like you have probably 1/2 of earning $0. You have probably 1/3 of getting $1 and probably 1/6 of getting $10. And just because of how the units work out, in the end, you're still gonna get units in dollars. So it's kind of giving you like what you're expected to get from this game. So it's like if you play this game for a long, long time, kind of like what you're on average, what are you gonna end up with? It's about $2. So you would not buy a share for $2.50 because on average you would lose about 50 cents every time you buy it, right? Because if you get only $2 and you put in 250, you kind of lose 50 cents. So like an important note is that the expected value is not necessarily like the most likely result. It's not going to be a specific result. It's not even going to be like a possibility because in this case, you can't even get $2, right? Like you can only get $1 and $10 or and $0. But it's simply like the average of the result if the event were to take place along. Okay. Any questions? Okay, so now we're gonna do some exercises. We have plenty of time, so I'll give like 3 to 4 minutes for every question. And then I'm going to also like ask people to give their thoughts on the question and provide the solution at the end. So let's all take a look at this question. Oh, yes, bye, Bobby. Sorry, I didn't see your hand earlier.
So what I was thinking is that there are a total of 36 like sums, I guess. But
Mm-hmm.
like not all of them are different, but there are 36 of them. And out of those, um, 5 of them add to 8 and then 4 add to 9. So it'd be
Mm-hmm.
9 over 36, like the probability of you walking the plank.
Great, great, yes.
But they're doing it alphabetically. And if the probability that all of them roll the dice once would be 3/4 times 3/4 times 3/4.
Mm-hmm.
And the other way Duck survives is if one player loses. So there are 3 other players who can lose before him.
Mm-hmm.
So I don't know. I don't know what to do after this.
Great, you are like almost there. So we have, okay, so we want to find the probability that Doug survives. So we can kind of, I think it's easier to calculate by finding the probability that he does not survive, right? So, um, if the probability that Doug dies is that he only dies if the others don't roll an 8 or a 9, right? And he does. So that exactly what you said, that's kind of like 3/4 times 3/4 times 3/4. And then the probability that he dies is 1/4, right? So what we want is this is him dying, right? And then all we need to do is subtract that from 1 to get our answer. So this is very critical. So like finding the 9 over 36, number of ways you can roll either an 8 or 9. And then this is like A, B, and C surviving, I guess. Because to survive, all you have to do is like not roll an 8 or a 9, right? And that's just 1 minus 1/4, which is equal to 1/3. So if we multiply, sorry, 1 minus 1/4, which is equal to 3/4. So, and we multiply 3/4 3 times to calculate the probability that A, B, and C all survive. And then we're trying to calculate the probability that Doug dies. So he has 1/4 chance of dying when it comes to his turn. So yeah, great job. That was super close. Any questions? All right, let's go on to the second one. Wait, let me see if we should do the second one or let's try, I think the second one is like super bashy. It's like a lot of casework. So let's try the third one first. The third one is, I think, a bit more difficult, but has like a, what is it? Like a neater solution. For this question, I would hint is set up P, so let P be the probability of not seeing a car in 5 minutes. And see how you can manipulate P to get that an equation, or to manipulate P to get an expression that is equal to 609 over 625. Because P is what we want, right? Like we want the probability of seeing a car within the next any 5 minutes. Oh, yes. Violet, please share your thoughts.
For this problem, you would use complementary probability. So since the probability that he sees a car within the next 20 minutes is 609 over 625, then if I take 1 and subtract that from 1, then that would be 16 over 625. Then I take the fourth root of this to find what would it be if he didn't see a car in 5 minutes. So then that's 2 over 5. So then I would take 1 and subtract from 1, 2 over 5. So the probability he does see a car within the next 5 minutes is 3/5.
Great, perfect. That is correct. So anyone have any questions? So basically, to calculate the probability that Richard does not see any car in the next 20 minutes is 16 over 625. And then we can set like, we know the probability of him not seeing a car within 5 minutes. We can use that probability and multiply it, or take the fourth root, take it to the fourth power to get the probability that he does not see a car in the next 20 minutes. So to go backwards, we just take the fourth root of that and then get 2/5. And then we want probability of him seeing a car in 5 minutes, so we subtract that again from 1 to get 3/5. Great. All right, so lastly, I'm just going to let you guys look at this question, and then we might not finish it because it's like has a super long was it like solution, but I'll definitely go through like the general pathway of how to solve this question.
Can you show the last slide one more time?
Oh yeah. All right, okay.
Are you gonna post the full solution to this question on the Google Classroom?
Yeah, I'll write it out after class and post it.
Okay, is this the last question we have?
Yeah.
Okay, thank you.
So for this question, I would do casework on Bullwinkle's larger number. So like, oh my gosh, okay, so you say like if it's 1, 2, 3, 4, 5, or 6. That's like the general idea, I think. Alright, so I've kind of like started the first one. So to explain this, what I'm doing is that, so if we consider the case where Bullwinkle's larger number is 1, for Bullwinkle to roll 1 as its largest number, it must roll 1 both times, right? Because there's no number that's smaller than 1. So for him or them to roll 1 as their larger number out of 2 rolls, they must roll 1 both times, and that happens with probability 1/6 times 1/6, which is 1/36. And then the probability that Rocky rolls once one number that's greater than that is probability 1, right? Because any number Rocky rolls will be greater than or equal to 1. So for that case, we have 1/36 times 1 as the final probability for that. And then you just kind of like count and do this for like all the probabilities. And then finally you like add them all together. Does that make sense for everyone? Alright, so if no one has any questions, then I'll finish writing this slide and then post it right after class. And if no one has any questions, then we'll end class today. Next class will be next week at the same time. I forgot what we're doing. I think we might be doing geometry. I don't know. But yeah. I'll see you guys next week. Thank you so much.
Thank you. Bye.
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 You bye.
Bye. Thank you.
Welcome. Bye bye.
Bye.
Bye bye.